We got started with some very basic combinatorics in an earlier session. I hope you are comfortable with the bunch of things that I have already covered with you on combinatorics. Are there questions from the same? Is there anything that's bothering you amongst the ones that we've done in the class, or are you all right? Now, have I discussed the principle of inclusion exclusion with you? Have I discussed pigeonhole principle with you? No. Now, number of elements in A union B, that means number of elements in A or B. Number of elements, union means A or B, is number of elements in A plus number of elements in B minus number of elements in A intersection B. If there are three sets A, B and C, then number of elements in A or B or C, which means number of elements in A union B union C, is number of elements in A plus number of elements in B plus number of elements in C minus number of elements in A intersection B minus number of elements in B intersection C minus number of elements in C intersection A plus number of elements in A intersection B intersection C, which in summation notation could be written as summation NA. That means all terms of the kind NA, which means NA plus NB plus NC. There would be, if there are three sets, then the number of terms in this summation is going to be 3C1. Number of terms in this summation is going to be from three things, taking one at a time, right? A, for example, B. And then, so these three terms are clubbed into a summation NA. If there are three sets, the number of terms in this summation is going to be 3C1 minus summation of terms of the kind A intersection B. See, this term and this term belong to this variety A intersection B, B intersection C, C intersection A, which would be of three sets you take two at a time. Of three sets you take two at a time. So there would be 3C2 terms in this summation. There is going to be 3C2 terms in this summation. And then terms of the kind A intersection B intersection C. So you might want to write just to bring about aesthetic looks in the entire expression. We write this as a summation A intersection B intersection C, which means terms of the kind A intersection B intersection C. If there are three sets A, B and C, there is only one term of this kind, which is this, right? So this would be 3C3, which is one term, right? There is just going to be one term here, right? This one is like minus 1 to power 3 minus 1, and this is minus 1 to power, this is minus 1 to power 3 minus 2, and then the signs alternate, as you can see, plus, minus, plus, the signs alternate. Now, if I have to go ahead and generalize this for n sets, if I have to go ahead and generalize the principle of inclusion and exclusion for n sets, for example, A1, A2, A3, An, if there are n sets, and I have to write this, this is called the principle of inclusion and exclusion for two sets, for three sets. So there is like, this is inclusion, there is exclusion, and there is inclusion, right? That's why it's called the principle of inclusion, exclusion. Now, in general, for n sets, the principle is let's say the sets are A1, A2, A3, An are the n sets. Number of elements in A1 or A2 or A3 or An. Number of elements in A1 or A2 or A3 or An A1 union A2 union A3 union AN. That is going to be summation NA1. So this summation would contain terms like NA1 plus NA2 plus NA3 plus NAN, right? So number of terms in this summation is going to be NC1 of n things taken one at a time, right? That would be the number of terms in this summation, NC1. The next summation would be terms of the following kind. Number of elements in A1 intersection A2. A1, A2, A2, A3, A3, A1 and so on and so forth. And the number of terms in this second summation is going to be NC2. Taking 2 at a time, the number of terms is going to be NC2. NC2 terms will prevail in this summation, right? Similarly, taking 3 sets at a time, number of terms in this summation is going to be NC3. Similarly, A1 intersection A2 intersection A3 intersection A4. Number of terms in this summation is going to be NC4. Taking 4 at a time, right? So signs will alternate and you keep moving. The sign here is like -1 to power 2 minus 1. The sign here is like -1 to power 3 minus 1. The sign here is -1 to power 4 minus 1. And going this way, you come up to the last term, which would be -1 to power n minus 1, because this is like n, A1 intersection A2 intersection A3 intersection AN. How many terms would be prevalent in this summation? NCN, that is just one term, right? So if you have n, the sign here is going to be -1 to power n minus 1. When you had 2, the sign was -1 to power 2 minus 1. When you had 3, the sign was -1 to power 3 minus 1, -1 to power 4 minus 1, -1 to power n minus 1. That's the scheme of signs in this bunch of summations that involve the union of these sets, right? And this, like I told you, is called the principle of inclusion exclusion. A very powerful tool in our digressions on combinatorics. It will help us count certain things with great amount of ease in a systematic manner, and we'll refer to this as pi, the sweetie pie. Now let's look at some very simple applications of pi, right? Very simple applications of pi. How many numbers from 1 to 1000 are neither by 5 nor by? How many numbers from 1 to 1000 are neither divisible by 5 nor by 7, right? Okay. First of all, number of numbers that are divisible by 5 is going to be the integer part of 1000 by 5. That is, there are 200 numbers that are divisible by 5 from 1 to 1000. Yes or no? Isn't it? There are 1000 by 5 integer part of this. That is 200 numbers that are divisible by 5 from 1 to 1000. Number of numbers that are divisible by 7. That's going to be the integer part of 1000 by 7. Yes or no? Isn't it? I hope all of you understand this. So that's going to be 142. The integer part is going to be 1000 by 7. The integer part is going to be 142. Right? How many numbers are divisible by 5 and 7? 5 and 7 means 35. Number of numbers divisible by 5 and 7 is number of numbers divisible by 35. That's going to be integer part of 1000 by 35. Right? 200 by 7 to 8. 28. 28 numbers from 1 to 1000 will be divisible by 35. Yes or no? Are you alright with this? So, number of numbers divisible by 5 or 7. From principle of inclusion exclusion, number of numbers divisible by 5 or 7 is going to be number of numbers divisible by 5 plus n7 minus n. 5 intersection 7. Clear? Which is going to be 200 plus 142 minus 28. Yes or no? So that makes it 1414. So 314. There are 314 numbers that are either divisible by 5 or by 7. From 1 to 1000 there are 314 numbers that are divisible by either 5 or by 7. So number of numbers that are divisible by neither 5 nor 7 is going to be 1000 minus 314. Yes or no? So 686 numbers would be neither divisible by 5 nor by 7. Yes or no, Manan? Right? 686 numbers would be divisible neither by 5 nor by 7. Clear? How very important thing in counting which I want to be able to teach you is the following. Suppose there are n letters designated L1, L2, L3, Ln. There are n letters designated L1, L2, L3, Ln. Right? And there are n designated envelopes. For letter L1, there is an addressed envelope, refer to that as E1. For L2, there is an addressed envelope, refer to that as E2, and so on and so forth. N addressed envelopes. Call them E1, E2, E3, En. These are the n addressed envelopes. That means L1 is meant to go into E1, L2 is meant to go into E2, L3 is meant to go into E3, Ln is meant to go into En. Question number 1. In how many ways can all the letters be put into the right envelope? There is only one way. There is only one way to put all letters into their corresponding envelope. All the letters into their right envelopes, there is only one way. We will also assume that in a given envelope, you are not submitting more than one letter. Right? There is one letter per envelope by default. That's the understanding. In how many ways In how many ways could I designate letters to envelope? In how many ways can I designate letters to envelope, different letters to different envelopes in general, such that no goddamn letter gets into the right envelope? Evil thought, right? When Khoka writes to Khoki, but it goes to some Boki, right? And we want that to happen. No letter getting into its designated envelope. In how many ways could I give shape to my evil designs of no letter getting into its right envelope? First of all, okay, forget this. Answer a simpler question first. In general, right or wrong, in how many ways could I delegate these letters to these envelopes arbitrarily? N factorial? In how many ways? I mean, let's say this, it's like these are n spaces in which these things have to be kept. So in how many ways can I arrange these n things into these n spaces? N factorial ways. The order is important, right? So total number of ways of delegating letters to envelopes is n factorial. Now, of these n factorial ways, there are some ways in which no letter would have gotten into its right envelope. For example, one way of ensuring no letter gets into its right envelope is like this going to E2, L2 going to E1, L3 going to En, Ln going to En minus 1 and so on and so forth, right? That's one of the ways of putting letters not in their right envelopes, right? How many such ways can I produce? How many such ways could I generate such that not a single letter gets into the right envelope? Okay, now total numbers are n factorial, that we understand. Total numbers are n factorial. Total number of ways of delegating letters to envelopes is n factorial. Now answer the following. Number of ways in which L1 gets into the right envelope. Hey, come on. Right, Kill. I mean, you're not going to just put L1 into the envelope and, give stepmotherly treatment to the remaining letters. You putting L1 into the right envelope in one way, but then there are more ways of designating the remaining letters in the remaining envelopes. So when I say L1 getting into the right envelope, that means a way in which L1 has gotten into its right envelope, others may or may not get into their right. So obviously, one way of putting L1 in E1, and then I have to put the remaining also in the remaining n minus 1 slots. So these remaining n minus 1 could be designated to these n minus 1 slots in n minus 1 factorial ways. So assign L1 to E1 in one way, into assign remaining n minus 1 things to the remaining n minus 1 spots in n minus 1 factorial ways. So this is going to be n minus 1 factorial, yes or no? Number of ways in which L1 could be assigned the right envelope is assign L1 and then assign remaining. That's the procedure to be adopted, right? Assign L1 and then assign the remaining. Assign L1 in one way, assign the remaining n minus 1 and n minus 1 factorial ways in the n minus 1 remaining spots. Clear? So I call this n L1 as n minus 1 factorial ways. Number of ways in which L1 gets into the right envelope is n minus 1 factorial ways, yes or no, right? Similarly, do you realize that this is also the same as the number of ways in which L2 gets into the right envelope? Put L2 in E2 and the remaining n minus 1 in n minus 1 spots can be done in n minus 1 factorial ways. Same thing. This is the same as NL3 and so on and so forth. Clear? Is there an issue with this? No. Number of ways in which L1 and L2 can get into the right envelope. Number of ways in which L1 and L2 can get into the right envelope. How much? N minus 2 factorial ways, very clearly. Put L1 in E1 and then L2 in E2, 1 into 1, and then the remaining n minus 2 in the remaining n minus 2 spots can be arranged in n minus 2 factorial ways. Clear? So, this is n minus 2 factorial ways. And this is the same as, let's say, number of ways in which L2 and L3 can get into the right envelope. This is the same as the number of ways in which L1 and L2, L3 can get into the right envelope, etc. This is the number of ways in which any two letters get into the right envelope. Others may or may not get into the right envelope, right? Number of ways in which L1 and L2 and L3 get into the right envelope, which is the same as the number of ways in which any three letters Li, Lj, Lk get into the right envelope. Number of ways in which any three letters Li, Lj, Lk get into the right envelope will be n minus 3 factorial. How about it? Going this way, number of ways in which L1 and L2 and L3 and Ln get into the right envelope. One way, just one way, right? So, this I can write as n minus n factorial ways, right? One way, which is 0 factorial n minus n factorial, just to bring symmetry in the representation, right? Now, no confusion, right? All of you are fine with this so far, right? Got me? Now, number of ways in which L1 or L2 or L3 or Ln right envelope is mathematically designated as L1 or L2 or L3 or Ln. Number of ways in which L1 or L2 or L3 or Ln gets into the right envelope, right? That's going to be from principle of inclusion and exclusion. That means this would give you the number of ways in which at least one letter would have got into the right envelope. L1 or L2 or L3 or Ln, at least one. There could have been more than one letter getting into the right envelope, but then at least one getting into the right envelope, that means L1 or L2 or L3 or Ln getting into the right envelope from the principle of inclusion exclusion is going to be summation NL1, right, minus summation N L1 intersection L2 plus summation N L1 intersection L2 intersection L3, going this way, minus 1 to power n minus 1 summation N L1 intersection L2 intersection Ln, right? That's the principle of inclusion and exclusion. Clear? Now, what is this? How many terms in this? NC1 terms, NL1 plus NL2 plus NL3 plus NLN, NC1 terms, and each of value NL1, each of value n minus 1 factorial, yes or no? There are NC1 terms prevalent in the summation and each of value equal to n minus 1 factorial. So then, this is like NC1 into n minus 1 factorial. Clear? Okay. How many terms in this summation? NC2 terms, taking 2 at a time, of n sets, taking 2 at a time, NC2 terms in this summation, and the value of each term is n minus 2 factorial, right? So NC2 into n minus 2 factorial. Similarly, plus NC3 into n minus 3 factorial minus NC4 into n minus 4 factorial. Going this way, minus 1 to power n minus 1 NCn into n minus n factorial. Just putting all terms in similar baskets, right? Clear? So what would this summation give me? This would give me the total number of ways in which at least one letter would have gotten into its right envelope. This, if I simplify it, realize that I could write this as n factorial by n minus 1 factorial, which will get cancelled with this, by 1 factorial. So the n minus 1 factorial from the numerator and denominator would cancel. Here also the denominator would be n minus 2 factorial into 2 factorial. The n minus 2 factorial will get cancelled. So this would be n factorial by 2 factorial. N factorial by n minus 3 factorial by 3 factorial, n minus 3 factorial would get cancelled, and so on and so forth. So this then assumes the following format: n factorial by 1 factorial minus n factorial by 2 factorial plus n factorial by 3 factorial going this way, minus 1 to power n minus 1 into n factorial by n factorial. Right? Which is there a confusion? Confusion hai kya? Which is like n factorial into 1 by 1 factorial minus 1 by 2 factorial minus 1 by 3 factorial minus 1 to power n minus 1 by n factorial, etc. This is the number of ways in which at least one letter would have gotten into its right envelope, right? And what are the total number of ways? N factorial was the total. There were total n factorial ways of delegating letters to envelopes, one letter per envelope. Out of n factorial, these were those many ways in which there was at least one letter getting into the right envelope. In these many ways of designating letters to envelopes, at least one letter would have gotten into its right envelope. That means from n factorial, if I remove these many ways, I will get the number of ways in which not a single letter gets into its right envelope. Yes or no? Right? So, number of ways in which no letter is total n factorial minus this. Oh, plus, sorry, 1 minus plus 1 by 3 factorial minus 1 by 4 factorial. These would give you the total number of ways in which not a single letter gets into the right envelope when you start to arrange L1, L2, L3 into E1, E2, E3, etc. Which is like n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial. The signs will alternate now and will change. When I plunge this minus into the parenthesis, all these signs will change. Eventually, I'll get like a minus 1 to power n by n factorial. This is the number of ways in which n letters could be put into n envelopes with no letter getting into its right envelope. So this is not like arranging n letters in n envelopes. We would call it deranging n letters in n. So this we would call not a case of arrangement but a case of derangement. So this is number of derangement of n things. And we call it derangement of n things, dn, derangement of n things. It used to happen. Okay, once you're done with this, I'll tell you where exactly it happens. At IIT, you know, we were always very short on cash. Students, how much money do you have? We used to wear those Hawaii slippers, Hawaii chappal. Not our very own, that too. And wear those to the point of extinction. In the sense, eventually, it used to get only few microns thick. The strap used to be fixed with the mother body with a safety pin. And then, when even those few microns vanished and our foot was in close contact with Mother Earth, that's when we decide to go to the computer center at IIT. Just outside the computer center, 100 people entering the computer center with their slippers outside. They go in with one pair, but they come out with some other pair. So the prime objective of going to the computer center was not academics, was finding a suitable pair of slippers. So 100 people getting into the computer center and 100 sets of slippers outside. You go in with one, but you never come out with your own envelope. You come out with some other envelope. So if you put n equal to 100, you will get the number of ways in which those 100 people would come out with slippers. Not even one person wearing his own slipper once he comes out. Right? So this happens. This is a very important concept, derangement, extremely important concept, and once I do functions for you, this will be used time and again. Even in basic combinatorics, there would be sophisticated problems that would require this concept of derangement. So remember this, very useful concept, right? Derangement of n things. Remember this series. Now, any natural number could be written as a product of powers of primes. What I mean is, you know, if you have, let's say, 100, n is 100. This could be written as 4 into 25, which is 2 squared into 5 squared. 2 is a prime, 5 is a prime, 2 to the power 2 into 5 to the power 2. If you had, let's say, 300, then in addition, you have 2 squared into 3 into 5 squared. 2 to the power something into 3 to the power something into 5 to the power something, right? So essentially, any natural number could be written as a product of powers of primes in a unique manner, right? Say n, a natural number n, let me assume that n greater than 1 could be written as some prime number p1 to the power alpha 1 into prime number p2 to the power alpha 2 into prime number pn to the power alpha n. P1, P2 are prime numbers. So you could factorize any number into a product of powers of primes in a unique manner, isn't it? So P1 to power alpha 1, P2 to power alpha 2, Pn to power alpha n, where alpha 1, alpha 2, alpha n are natural numbers. Alpha 1, alpha 2, alpha n are natural numbers, but P1, P2, P3, Pn are prime numbers. Product of powers of primes. Any natural number could be expressed this way. Clear? Now, if I am seeking a factor of n, if I am seeking a factor of n, that means a divisor of n. If I am seeking a divisor of n, call it f. F is a certain factor of n or divisor. This is a certain divisor of n. A divisor of n would be of the form, it will have the same prime factors. A divisor of n will have the same prime factors but raised to smaller powers, That means it's going to be, let's say, P1 to the power beta 1 into P2 to the power beta 2 into Pn to the power beta n. You know what I'm saying? Where beta 1 has to be less than or equal to alpha 1. Beta 2 has to be less than or equal to alpha 2. Beta n has to be less than or equal to alpha n. Why? Because when you divide n by f, you should get an integer, When you divide n by f, you should get an integer because f is a factor of n. That means P1 to power alpha 1 divided by P1 to power beta 1 will be an integer if alpha 1 is greater than or equal to beta 1. Yes or no? P2 to power alpha 2 divided by P2 to power beta 2 would be an integer if alpha 2 is greater than or equal to beta 2. Yes or no? Right? And so on and so forth. So then, if f is a factor of n, then it should have the same prime factors, as n, and should be raised to powers not exceeding the corresponding powers prevalent in n. That means beta 1 can assume values like beta 1. What are the values that beta 1 can assume? Beta 0, it could be 0, alright. 1, 2, 3 up to alpha 1. These are the values that beta 1 can legitimately assume. 0, 1, 2, alpha 1. That means each time you select one of the values of beta 1 from this set, you are actually initiating a process of finding one of the factors of n. Right? One of the factors of n would be installed if a certain beta 1 is selected from this set. Right? That means how many ways of selecting beta 1? Alpha 1 plus 1 ways of selecting beta 1, right? Alpha 1 plus 1 ways of selecting beta 1. Is it not? Okay. Beta 2 again can assume values like it cannot exceed alpha 2 because this by this has to be an integer. So beta 2 cannot exceed alpha 2. So beta 2 will assume values like 0, 1, 2, 3 up to alpha 2. How many ways of selecting beta 2 therefore? Alpha 2 plus 1 ways of selecting beta 2. Alpha 2 plus 1 ways of selecting beta 2. Is that alright? Going this way. Beta n can assume how many values? 0, 1, 2, 3 up to alpha n. So beta n assumes values from the following set 0, 1, 2 up to alpha n. That is alpha n plus 1 ways of selecting beta n. Now, to create a factor f of n, to create any one factor f of n, you can select any beta 1 from this set, any beta 2 from this set, any beta 3 from this set, any beta n from this set. So, essentially the whole process of producing a factor f is like selecting beta 1, beta 2, beta 3, beta n. Simultaneously, beta 1 and beta 2 and beta 3 and beta n. The number of ways in which you could select beta 1 and beta 2 and beta 3 and beta n would give you the number of factors f of n, will give you the number of factors f of n, right? Isn't it? So, the number of factors f of n is like from the fundamental principle of counting. The first thing that you do is select beta 1. In how many ways can you select beta 1? Alpha 1 plus 1 ways. In how many ways can you select beta 2? Alpha 2 plus 1 ways. Similarly, in how many ways can you select beta n? Alpha n plus 1 ways. So, these are the beta 1 and beta 2 and beta 3 and beta n. That's why we multiplied, right? So, these are the number of ways in which we could select different combinations of beta 1, beta 2, beta 3, beta n. And number of ways we could select beta 1, beta 2, beta 3, beta n will produce that many factors of n, will produce that many factors of n, yes or no? So, this alpha 1 plus 1 into alpha 2 plus 1 into alpha n plus 1 will be the number of factors f of the natural number n, right? And it includes one case where beta 1 is 0, where beta 2 is 0, where beta n is 0. That means it includes a case where f is 1. It includes a case where a factor is 1. These are the total number of factors. It includes 1 as a factor. It also includes the case where beta 1 is alpha 1, beta 2 is alpha 2, beta n is alpha n. That means beta 1 is alpha 1, beta 2 is alpha 2, beta n is alpha n. That means it includes one case in which f is equal to n. So, this count, this product represents the total number of factors f of n, which includes 1 and it includes n of the factors. Yes or no? Right? Got me? Now, once we have the total number of factors f of n, these are the total number of factors f of n. I want to be able to find the sum of all the factors of n. I want to be able to find the sum of all factors of n, right? No confusion, right? All of you there with me? Who? Pn. Yeah. But that case is included where beta 1, beta 2, etc. are 0 and beta n is 1. F is less than? No, how can it be? F can't be less than Pn? No, because it's, no, how can it be less than Pn? I mean, what, okay, so what? F can be less than, okay, F can be less than Pn where beta n is 0, for example, yeah, where beta n is 0. That's the only way F can be less than Pn, isn't it? Because then, maybe you know, beta 2, beta 3, beta n are all 0 and beta 1 is 1 and we get P1 and P1 is less than Pn. So, F can be less than Pn, but that case is included in that count, isn't it? The case where beta 2, beta 3, beta n are all 0 and beta 1 is 1. That's the case where you get a factor P1 which is less than Pn. So, F, a factor less than Pn is obtained that way, isn't it? Do you have questions? No? Now, I want to find the sum of all these factors of n. How many factors in all? Alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 plus 1 into alpha n plus 1 are the total number of factors including 1 and n. I now want to add all these factors. I want to add all the devices including 1 and n. That's my, that's the next task in hand, right? Look at the following. Look at this product. Look at this product, this into this, etc., up to this. Look at this product of terms. Just observe this product of terms. I take the prime number P1, P1 to power 0, P1 to power 1, P1 to power 2, P1 cube, P1 to power alpha 1, going all the way till alpha 1. Different powers of P1 are included here. From 0 all the way to alpha 1. Different powers of P2 are included here from 0 all the way to alpha 2. Different powers of P3 from 0 all the way to alpha 3. Different powers of Pn from 0 all the way to alpha n. Now, if you choose to multiply this out, first of all, how many terms will be produced when you multiply this out? If you multiply this out, how many terms will be produced? Hey, if there is like 2 plus 1 plus 5 into 3 plus 6 plus 2 plus 9, how many terms will be produced? No. 3 into 4, 12 terms will be produced in this multiplication, isn't it? 1, 2, 3 into 4, 12 terms will be produced when I multiply this out. And then 1 plus 5 plus 2 plus 9 plus 11. How many terms will be produced when I multiply this out? 3 into 4 into 6 into 5. Yes or no? 60 terms will be produced. Isn't it? So one thing, when I multiply this whole thing out, how many terms are produced? This is like, how many terms here? Alpha 1 plus 1 terms. How many terms here? Alpha 2 plus 1 terms here. How many terms here? Alpha 3 plus 1 terms here. How many terms here? Alpha n plus 1 terms. Hey, one thing for sure, the total number of terms produced when you multiply this out and spread the terms out, when you multiply the whole thing and spread the terms out, then this would be the total number of terms generated. But then do you realize that this is the total number of factors f of n? This is also the total number of factors f of n, yes or no? You know what I'm saying? And now look at any sample term. Look at any sample term. Let's say I take a term from here, P1 to power gamma 1, where gamma 1 can assume any value from 0 to alpha 1. A sample term in this product. a sample term in this product is, one sample term, there are these many terms and all when you multiply the whole thing out. A sample term is one of the terms P1 to power gamma 1, for example, where gamma 1 can assume any value from 0 to alpha 1. Gamma 1 can assume any value from 0 to alpha 1. Then look at a term here, P2 to power gamma 2, where gamma 2 can assume any value from 0 to alpha 2. So, into P2 to power gamma 2. And then a P3 to power gamma 3, where gamma 3 can assume any value from 0 to alpha 3. Pn to power gamma n. This is a sample term. This is a sample term. Where and how many such terms are produced? These many such terms are produced. These many such terms are produced by, now gamma 1 can take any value from 0 to alpha 1. Gamma 2 can take any value from 0 to alpha 2. Gamma 3 can take any value from 0 to alpha 3. Gamma n can take any value from 0 to alpha n, right? If that be the case, that means this is one sample term. This is one sample term. Do you realize that since gamma 1 is always less than or equal to alpha 1, gamma 2 is always less than or equal to alpha 2, gamma 3 always less than or equal to alpha 3, gamma n always less than or equal to alpha n. This is a factor f of n, yes or no? So any term produced in this multiplication will be a factor of n. Any term produced in this multiplication will be a factor of n, yes or no? Do you realize that? And then you multiply the whole thing out, you will get sum of the factors f of n. When you multiply the whole thing out, you will get sum of terms of this kind. You will get sum of terms of this kind, yes or no? Which means sum of the factors of n. Which means sum of the factors of n. When you multiply the whole thing out, you get a large number of terms which when added will give you the sum of the factors of n, because on multiplication you are only getting factors f of n. Are you confused? No. So this product actually is the sum of the factors of n. This product, this into this into this into this, is sum of the factors f of n, yes or no? Are you there with me? This is a sample term which is a factor of n, and all terms produced in this multiplication would be of this kind. So you will get sum of factors f of n, and these many terms are produced, which exactly matches with the number of factors of n. Clear? So this product, if I evaluate this product, it will give me the sum of the factors of n. And what is this factor? What is this sum? Do you realize that this is a GP series with common ratio P1 and number of terms alpha 1 plus 1? Yes or no? This sum is a GP series with common ratio P1 and number of terms alpha 1 plus 1. Yes or no? Right? So what is this supposed to be? A, which is 1, into r to the power n, n is alpha 1 plus 1 minus 1 divided by r minus 1. That's this. Sum of this GP series. What is the sum of this GP series? P2 to power alpha 2 plus 1 minus 1 by P2 minus 1, common ratio P2, number of terms alpha 2 plus 1, first term 1. Right? Going this way, P3 to power, rather Pn to power alpha n plus 1 minus 1 divided by Pn minus 1. What would this give me? This entire thing, this product will give me the sum of the factors f of n. And realize that it includes in the sum of the factors of n, it includes P1 to power 0, P2 to power 0, Pn to power 0, which means it includes 1. It also includes in this sum, it includes P1 to power alpha 1 into P2 to power alpha 2 into P3 to power alpha 3 into Pn to power alpha n, which is n. So this is the sum of the factors of n, including 1 and n, including 1 and n. Clear? This product will represent the sum of the factors f of n including 1 and n. Clear? Is there a confusion? Have you all understood this? Now, say I give you n digits. A1, A2, A3, AN. These are n digits. A1, A2, A3, AN. And I want to create n digit numbers. I want to create n digit numbers from the digits above. N digit numbers from the digits above. In two possible ways. One, where I allow repetition of a digit in creating a number. Two, in which I don't allow repetition of a digit. Right? Let's say case 1, when in producing a n digit number, in producing a n digit string, I allow repetition. That's case 1, right? Repetition allowed. Where if in the units digit, if in the units place I have used A2, then in the hundreds place also I could use A2 if I like. Right? That's what I mean by permitting repetition and producing a string, n digit string. Clear? So I want to generate all n digit numbers from these n digits, permitting repetition of digits in the numbers, right? After having generated all the n digit numbers with repetition allowed, I want to add all these numbers. That means sum of all these numbers is what I am seeking. Sum of all the numbers I am producing in this process, n digit numbers that I am producing in this process is what I am seeking. Clear? Now, this is the n digit number, n spaces. This is a certain n digit number. Units place, tens place, hundreds place, and so on and so forth, right? Okay. Suppose I fix A1 here in the units place. Suppose I fix A1 in the units place. In how many ways can I fill up the remaining n minus 1 places? Right. Obviously, just because I have filled up A1 here does not mean that I can't fill up A1 anywhere else. That means for each of these spots, I still have n possible ways of filling up each of these spots. I'm not restricted here, right? So the number of ways I can fill up this spot is n ways. Number of ways I can fill up this pot is n ways. Number of ways I could fill up this is n, and this n, and this n. So then, after fixing A1 in the units place, the number of ways in which I could fill out the remaining spaces is n into n into n into n, n minus 1 times, n into n into n, n minus 1 times. So that makes it n to power n minus 1. That makes it n to power n minus 1 ways, right? So, number of numbers with A1 in the units place is n to power n minus 1. I'm sorry. No, n into n into n, n minus 1 times. So n to power n minus 1. N to power n minus 1. Damn thing. Right? N ways of filling up this, n ways of filling, this is n into n into n, n minus 1 times. So that makes it n to power n minus 1 ways. So number of numbers with A1 in the units place is n to power n minus 1, right? Number of numbers similarly with A2 in the units place is also n to power n minus 1, right? You fix A2 here, and then the number of ways in which you can fill out the remaining spots is n to power n minus 1, yes or no, right? Number of numbers with an in the units place, is also n to power n minus 1, yes or no? Huh? So with A1 in the units place, I have these many numbers. With A2 in the units place, I have these many numbers. With AN in the units place, I have these many numbers. Now, if I have to add all the units spot, if I have to add all the units place of all these numbers produced, so with A1 in the units place, if I add all the A1s, it's going to be A1 into n to power n minus 1. And then I populate the A2s, and I add all the A2s in the units place, it's going to be A2 into n to power n minus 1, because A2 appeared these many times. So sum of all the A2s is going to be A2 into n to power n minus 1. And then I collect all the numbers with an in the units place and I add all the ans. How many ans are there? These many. So if I add all the ans, then it's going to be an into n to power n minus 1, right? So which means P is sum of all digits in the units place, which is A1 into n to power n minus 1, A2 into n to power n minus 1, An into n to power n minus 1. No? Are you confused? No? So which is like n to power n minus 1 into A1 plus A2 plus An. This is sum of all, P is the sum of all the digits in the units place, right? P is the sum of all the digits in the units place of all the numbers that are produced with repetition allowed. Clear? No confusion. So P we have now in place, sum of all the units place, right? Okay, now how many numbers with A1 in the tens place will exist? N to power n minus 1. You fix A1 in the tens place, you will have n to power n minus 1. How many with A2 in the units in the tens place? N to power n minus 1. An in the tens place, n to power n minus 1. Which means if you add all the digits in the tens place also, you will still get P. If you add all the digits in the hundreds place, you will still get P. If you add all thousands place, you will still get P, and so on and so forth. Yes or no? Right? Where P is known to us, right? Which means if I have to add systematically all these numbers, add all the units place, that's going to be P1. Tens place, it still adds up to P1, but it's going to be 10 P1. It's going to be 10 P1 because it's in the tens place. So it's going to become 10 times P1. In the hundreds place, then it's going to be 10 squared P1. In the thousands place, 10 cube P1. First place, 10 to power 0. Second place, 10 to power 2 minus 1. Third place, 10 to power 3 minus 1. Nth place, 10 to power n minus 1. That's the process of addition. Yes or no? So this would be the sum of all the numbers. This would be the required sum. S then would be P1 into 1 plus 10 squared plus 10 to power n minus 1, which is what? A GP series with common ratio 10, number of terms n. So then this is like P1. I'm sorry, I've not used P1, I've used P. So just call it P. P into 10 to power n minus 1 by 10 minus 1, which is P into 10 to power n minus 1 by 9. This is sum of all the numbers produced out of these digits with repetition allowed. You look a little baffled. No. Where P we understand is n to power n minus 1 into A1 plus A2 plus An. Clear? Now, case 2 where I don't allow for repetition. AQ. So now, repetition not allowed. Case 2. Repetition not allowed. How many numbers with A1 in the first place here? If I fix A1, in the units place, n minus 1 factorial, because I have remaining n minus 1 digits to be placed in these n minus 1 slots, and that can be done in n minus 1 factorial ways. N minus 1 factorial ways, yes or no? Which is the same as n into n minus 1 into n minus 2, etc. will give you n minus 1 factorial, right? Clear? So then, with A1 in the first place, A1 in the units place, I have n minus 1 factorial numbers produced. N minus 1 factorial numbers produced. With A2 in the first place, units place, I have n minus 1 factorial numbers produced. Same way. With An in the units place, how many numbers are produced? N minus 1 factorial numbers are produced. No? Are you lost? Now, if P is the sum of all the digits in the units place like before, right? P is the sum of all digits in the units place of the various numbers produced. Then that's going to be A1 appearing n minus 1 factorial times, so A1 into n minus 1 factorial. A2 appearing n minus 1 factorial times, so A2 into n minus 1 factorial. An into n minus 1 factorial. So sum of all the units place is going to be n minus 1 factorial into A1 plus A2 plus An. No? call it P. P is the sum of all the digits in the units place. And the same thing will hold good for the tens place. P will also be the sum of all the digits in the tens place, in the hundreds place, in the thousands place, and so on and so forth. So the required sum is going to be P plus 10P plus 10 squared P plus 10 to power n minus 1P. That's going to be the sum of all the numbers produced with repetition not allowed. Clear? Which is what? Which is P into 10 to power n minus 1 divided by 9, sum of a GP series 10 to power 0 plus 10 to power 1 plus 10 to power 2 plus 10 to power n minus 1, etc. Clear? Make sense to all of you? Another fundamental rule involved in all of counting, and it's the simplest of all the counting measures that you're going to learn. Suppose there are M pigeons. M pigeons. You can take M dogs also, that will not make a difference. And there are N pigeonholes. And you are not going to place cows in these pigeonholes. P1, P2, PM are the M pigeons, right? And these are the pigeonholes. H1, H2, Hn. N pigeonholes. These are the N pigeonholes. And M greater than N. Number of pigeons exceeding the number of pigeonholes. Number of pigeons exceeding the number of pigeonholes. Right? And you want to place pigeons in the pigeonholes. It's not like P1 is meant for H1 like the letters and the envelope, right? P1 can be placed anywhere, P2 can be placed anywhere, and in a given pigeonhole, you may not place a pigeon. In a given pigeonhole, you can place more than one pigeon, and so on and so forth, right? And if M is greater than N, then there must be at least one pigeonhole with more than one pigeon, isn't it? There must be at least one pigeonhole with more than one pigeon, because the number of pigeons exceed the number of pigeonholes. Clear? This is pigeonhole principle. This is pigeonhole principle. If M is greater than N, there must be at least one pigeonhole with more than one pigeon. सोच रहे हो बेवकूफ बना रहा है साला, ये कोई प्रिंसिपल है, कोई भी बच्चा बता देगा. There are at least two people in this class born on the same day of the week. There are at least two people in this class born on the same day of the week. The days of the week are Monday, Tuesday, Sunday. Right? 7 days. More than 7 people. You push people into their corresponding slots based on the day on which they are born. Do you realize that there would be at least one slot with more than one person? So there must be at least 2 people born on the same day of the week in this class. Yes or no? They must be. So then, the people in the class are the pigeons and these are the pigeonholes, right? There must be at least 2 people in the city of Kolkata born in the same year. Same year. There must be at least 2 people in the city of Kolkata born in the same year. Okay. What must be the oldest guy in this city of Kolkata? Huh? 100 years? Chalo aur bhi zyada dekh lo. One Sadhu Baba, some 10,000 years of tapasya. Right? बड़ा बड़ा जटाए रहेगा उसका 10,000 साल का एक साधु बाबा है. He must be the oldest guy, right? So then, what are the various ages possible? If 10,000 is the oldest, 10,000 or maybe 1 lakh year old, maybe 1 lakh year old. So then, the various ages are 1 year old. We are not talking about those who are about to come. All right, it's going to get very complicated. So we'll look into that sophistication at some other point of time in our leisure time. But 1 year old, and then there are 2-year-old people, 3-year-old people, and then a few Sadhu Babas, maybe 1 lakh year old. Maybe 1 lakh year old. These are all the possible ages that are prevalent in the city, right? How many people are there? More than 1 lakh. Number of pigeons? More than 1 lakh. The people are the pigeons. These are the pigeonholes. Do you realize that one of these would have to be at least occupied by more than 1 person? That means there must be at least 2 people born in the same year. Pigeonhole principle. Alright, that's pigeonhole principle. Now, suppose this is a square, a 2 by 2 square. This is a 2 by 2 square. This is a 2 by 2 square. And there are 5 dots available. 5 dots available. I pick 1 dot at a time and place it randomly in the square. Place it randomly in the square. Throw it randomly in the square. I throw these 5 dots randomly in the square. Right? So there are 5 positions occupied in the square. There are 5 positions occupied in the square. 1 per dot. Right? Some of these 2 dots could occupy the same position also. Right? Now, my claim is, no matter how you throw the dots in the square, no matter how you throw the dots in the square, there must be, irrespective of the clumsiness you deploy in throwing the dots, there must be at least 2 dots. There must be 2 dots in every mode of throwing the dot. There must be at least 2 dots. Or rather, there must be 2 dots such that the distance between them does not exceed root 2 units. Such that the distance between them does not exceed root 2 units. There must be at least 2 dots such that the distance between them does not exceed root 2 units. Existence of 2 such dots is guaranteed no matter how you fling these dots in the square. Right? How? Break this 2 by 2 square into 4 1 by 1 square. 4 1 by 1 square. Right? 4 pigeonholes. 5 pigeons. 4 pigeonholes, 5 pigeons. At least 1 pigeonhole must have 2 pigeons. There must be at least 1 pigeonhole having more than 1 pigeon. Right? So, at least 2 of these dots, must lie in the same sub-square. At least 2 of these dots must lie in the same sub-square, yes or no? So two of these dots lying in the same subsquare. At least two of these dots lying in the same subsquare, courtesy pigeonhole principle. And then, what's the maximum distance between any 2 points in the square? Root 2. So the distance between these two dots cannot exceed root 2. The distance between these two dots cannot exceed root 2. So no matter how you choose to fling these dots in the square, you would always end up getting at least two dots such that the distance between them does not exceed root 2 units. That's pigeonhole principle. Right? The point is, the principle is simple. It's like you have to identify who you want to treat as pigeons and where your pigeonholes lie. That's the whole thing. You know, having an eye for pigeons and pigeonholes is the key to applying pigeonhole principle. Right? No one would tell you, these are the pigeons and there lie your pigeonholes. Right? That would have to be obtained all by your own thought and common sense. Pigeonholes and pigeonhole principle. This seems so simple, but trust me, the best of situations in combinatorics are dealt with the help of pigeonhole principle. The best of problems are really out of pigeonhole principle. In most of these cases, again, identification of pigeons and pigeonholes could get kind of steep, right? Otherwise, once you've identified the pigeons and pigeonholes, it's straightforward, right? So that's yet another thing in all our learning on counting. So far so good. You understand everything, right? Now, even before, there is a host of other things that I have to teach in combinatorics. I have not even touched one pebble on the ocean, on the shore. In fact, we still have to pick the pebbles on the shore and then take a dip in the ocean. Long way to go. But then, even before I venture into more concepts, I want you to get familiar with some basic ways of solving problems, some mental familiarity towards some very simple things. And therefore, I passed on a very, very simple sheet across to you. And I'll look upon this sheet as an illustration, and we'll together solve the sheet. Off, on. Right. So, the sheet titled Slightly More Than Ground State. Alright. Problem 1. Number of ways in which 7 distinct toys could be distributed. These are the 7 distinct toys. T1, T2, T7. And there are 3 children, C1, C2, C3. Is what? Each of these toys could be given to any one of the 3 children, right? So T1 could be given in 3 ways, right? T2 can also go in 3 ways. T3 would also go in 3 ways. T7 can also go in 3 ways. So the number of ways is number of ways of giving away T1 into number of ways of giving T2 into number of ways of giving T3 into number of ways of giving Tn. So that makes it 3 to the power 7. 3 to the power 7 ways of distributing toys to children. It's possible that a child gets nothing, right? Now, if there are n things, let's say A1, A2, A3, AN, if there are n things, alright, and you want to create subsets out of these n things, you want to create subsets out of these n things. The subsets could be of various sizes. It could be of size 0, null set. That's a null set, right? But subset could be of size 1, or size 1, that means A1 could be one subset, A2, A3, AN, right? N subsets of size 2. And then there are subsets of size 2, A1, A2, A2, A3, which is like NC2 subsets of size 2. Then there are subsets of size 3, A1, A2, A3, A2, A3, A4, A1, A3, A6. How many terms would be there in that subset? NC3 terms, right? NC3 such subset, NC3 such subset. You know what I'm saying? So subsets of various sizes could be created out of n things. Subsets of various sizes could be created out of these n things. Now, question is, how many subsets are there? How many subsets are there? Now, to create a subset, any subset, if I am creating a subset, either I am including a certain element or I am not including a certain element in creating a subset, right? Either I am including a certain element or I am not including a certain element. So, to create a subset, either I include A1 or I don't include A1. So, then two ways of dealing with A1. Either I include A2 or I don't include A2. So, two ways of dealing with A2, two ways of dealing with A3, two ways of dealing with AN. So, to create subsets, I am actually dealing with A1, A2, A3, AN, and number of ways in which I could deal with A1, A2, A3, AN with a view to either include them or not include them will give me the total number of subsets that I could produce. So, the total number of subsets that I am producing is 2 to the power n, which includes a subset in which A1, A2, A3, AN, none of them is included, That's a null set, right? It includes a subset in which all are included, A1, A2, A3, AN. So then these are the total number of subsets of various sizes, size 0, size 1, size 2, size 3. Size means number of elements in a subset, right? These are the total number of subsets that could be produced out of these n elements. These are the various total number of subsets that could be produced out of these n elements. Which is also the same as number of subsets of size 0 would be NC0, right? Number of subsets of size 1 would be NC1. You take one element at a time, you will get NC1 subsets. Number of subsets of size 2 would be NC2, right? Taking n things, out of n things, take 2 at a time. In how many ways can you do that? Will give you number of subsets of size 2, NC2. Number of subsets of size 3 would be NC3. Number of subsets of size n would be NCn. This will give me all possible subsets, size 0, size 1, size 2, size 3, size n, that could be generated out of these n elements, A1, A2, A3, AN. And this must be 2 to the power n, this must be 2 to the power n. Total number of subsets is 2 to the power n. So now this is important. NC0 plus NC1 plus NC2 plus NC3 plus NCn will be 2 to the power n, right? Now, come to the next problem. There are 2n plus 1 elements in this case, A1, A2, 2n plus 1 elements. What are the total number of subsets here? 2 to the power 2n plus 1. 2 to the power 2n plus 1 elements in all. 2 to the power 2n plus 1 subsets of various sizes. Size 0, size 1, size 2, size 3, etc. Size 2n plus 1. Now, number of subsets of size 0 would be NC0. Right? Number of subsets of size 1 would be NC1. Of size 2, NC2, I'm sorry, 2n plus 1. 2n plus 1, C0. 2n plus 1, C1. 2n plus 1 elements here, by the way. So, 2n plus 1, C2. 2n plus 1, Cn. 2n plus 1, Cn plus 1. 2n plus 1, Cn plus 2. 2n plus 1, C, 2n plus 1. This is subsets of size 0 of 2n plus 1 things, taking 0 at a time, taking 1 at a time, taking 2 at a time, taking n at a time, taking n plus 1, n plus 2, n plus 3, 2n plus 1 at a time, right? Just prior to this, it's going to be 2n plus 1, C, 2n, right? This would give me the total number of subsets of various sizes that I could generate out of these 2n plus 1 elements. Does it make sense to you or not? Does it make sense to you or not? Right? And all of this must add up to 2n plus 1. Like before, instead of n, now you have 2n plus 1. That's the only difference, right? What we are seeking is total number of subsets of size of having more than n elements. Total number of subsets having more than n elements, right? That means what we are seeking is this. N elements means it could have n plus 1 elements, n plus 2 elements, n plus 3 elements, 2n plus 1 elements, right? So, the sum that we are seeking is number of subsets of size more than n, right? Having more than n elements is 2n plus 1, C n plus 1, 2n plus 1, C n plus 2, 2n plus 1, C n plus 3, 2n plus 1, C 2n, 2n plus 1, C 2n plus 1. That's the summation that we are seeking. Thank you. Now, did I tell you that NCR is the same as NC n minus R? No. NCR is the same as NC n minus R, right? NCR, this is NC, 2n plus 1 minus n plus 1. That means 2nc n. 2n plus 1 minus n plus 1 is n. 2ncr would be 2nc, this minus 2n plus 1 minus n plus 1. That is n, yes or no? This could be written as 2n plus 1 c n plus 2 is like 2n plus 1 c, this minus this, that means n minus 1. Right? 2n plus 1 c n minus 2. Going this way. 2n plus 1 c 1, 2n plus 1 minus 2n 1, and then 2n plus 1 c 0. Yes or no? You know what I'm saying? Hey, what it really boils down to is the terms are, if this is S, this is also S. If this is S, this is also S, right? So then 2 times S would be, look at the following. 2n plus 1 C0 plus 2n plus 1 C1 plus 2n plus 1 C2 plus 2n plus 1 Cn plus 2n plus 1 Cn plus 1 plus 2n plus 1 Cn plus 2 plus 2n plus 1 Cn plus 3 plus 2n plus 1 C 2n plus 1, which is actually 2 to the power 2n plus 1, yes or no? You know what I'm saying? If you add the two S's, then you simply get the sum that you see here, which is 2 to the power 2n plus 1, right? So this is 2 to the power 2n plus 1. So S is what we are seeking, which is 2 to the power 2n. All this I did only to keep you a little more involved. But I'll tell you something. What I would have done is, the total number of subsets are 2 to the power 2n plus 1, and think about it, 2 to the power 2n plus 1, half of them would be more than n elements, half of them would be less than n elements, would be n or less. Half of these would be more than n elements, the remaining half would be n or less elements. So half of this is half of 2 to the power 2n plus 1, that is 2 to the power 2n. Right? But otherwise, for the time being, understand this and then go back and think about what I just said. But let's move on to the next problem. I hope all of you have understood this working. Right? Let's look at number 3. A is a set containing n elements. A is a set containing n elements. A subset P of A is chosen. A subset P of A is chosen. I pick a certain number of elements. Here and I create a subset. And after having used up some elements from A, I replenish those elements. Suppose to create a subset, I use up A1, then I replenish A with A1. That's what's done. The set A is reconstructed, right? When you create a subset, this is the procedure involved here. When you create a subset, you take a certain element and you've taken A1 from this set to create a subset. And then you, after having created the subset, you bring back, you restore an A1 in the set A so that the set A is brought to its original state. So a subset P is created. A subset P is created by restoring A after having created P, right? And then a subset Q is created again. A subset Q is created again. Again, after you create a subset Q, and again Q would be created from the same set of elements because I have replenished those elements in A, right? I have replenished the elements of A that I have used up in creating a subset P, right? So the set A is the same. The set A is the same as it was at the time when you constructed P. So now from the same set of elements you create a subset Q. From the same set of elements you create a subset Q. Now, in how many ways can I create these subsets P and Q such that P intersection Q is exactly 2 elements? The number of elements common to P and Q would be 2. Number of elements common to P and Q would be 2. Okay. First of all, in how many ways can I create exactly 2 common elements? NC2. Any 2 of these elements could be common between P and Q. Any 2 of these elements could be common between P and Q. That's the first thing. That has to happen, right? So the number of common elements between P and Q is number of ways in which 2 common elements could be selected as NC2. Yes or no? Number of ways in which common elements could be selected as NC2, clear? 2 common elements. And how many ways can we create those 2 common elements between P and Q? NC2 ways, right? Yes or no? So after having chosen those 2 elements that belong to P as well as Q, I have chosen 2 elements that will belong to P as well as Q, right? These are the 2 common. In how many ways could it be done? NC2. For example, A1 and A2 could both belong to P. A1 and AN could both belong to P. A2 and A5 could both belong to P. number of ways in which I could select two elements that belong to both P and Q is NC2, right? Isn't it? Now, after having chosen those two elements which are common to P and Q, how many elements remain in my endeavor to create a subset? N minus 2 elements remain, right? The remaining N minus 2 elements are, let's say, A1, A2, A3, An minus 2, right? Two elements for P and Q have already been selected, and that could be done in NC2 ways. These are the two common elements, right? These are the remaining elements. These are the remaining elements. I have to now learn to deal with these two elements in my construction of the subset P and Q. And I got to make sure that if a certain element belongs to P, it does not belong to Q. If a certain element belongs to Q, it does not belong to P. Or a certain element belongs to neither P nor Q. These are the only three ways I can deal with any element, right? So with A1, for example, in how many ways can I deal with A1? See, now I have to either give A1 to P or to Q. And or I give A1 to neither P nor Q. In how many ways can I deal with A1 then? Three ways. Either I give it to P, or I give it to Q, or I give it to neither P nor Q. I can't give it to both P and Q, because otherwise P and Q would have three common elements. In addition to this too, there would be A1 also. You know what I'm saying? So the number of ways of dealing with A1 is 3. Number of ways of dealing with A1 is 3. Are you alright with this? Either I give it to P, or I give it to Q, or I give it to neither P nor Q. Clear? In how many ways can I deal with A2? 3 ways. Either I give it to P, or I give it to Q, or I give it to neither P nor Q. How many ways can I deal with A3? 3 ways. In how many ways can I deal with An minus 2? 3 ways. So 3 into 3 into 3 into 3, that makes it 3 to the power n minus 2 ways of dealing with the remaining n minus 2 elements. So then first, what's the operation involved? I select the two elements. The two elements are given to both P and Q. And then in my creation of the subsets P and Q, I start dealing with these elements one at a time. 3 ways of dealing with this, 3 ways of dealing with this, 3 ways of dealing with this. In all, 3 to the power n minus 2 ways of dealing with the remaining in my production of the subsets P and Q, such that P and Q have no more than, have exactly 2 common elements, Are you alright with this? So this would be the number of ways in which I could create subsets P and Q having exactly 2 common elements. Clear? Are you lost? No. Makes sense to you? So NC2 into 3 to the power n minus 2 ways of producing subsets P and Q having exactly 2 common elements. क्या बात है बंदर? हाँ? तो fourth. Now, number of ways of selecting 4 numbers from 1 to 30. Four elements from 1 to 30 so as to exclude every selection of 4 consecutive elements. First of all, to select 4 elements, in how many ways can I select 4 elements? 30C4. 30C4 are the number of ways in which I can select 4 elements from these 30, 4 numbers from these 30. Now, in how many ways I have 4 consecutive elements, 4 consecutive numbers included? 27, right? 4 consecutive numbers. For example, I can have 1, 2, 3, 4. I can have 2, 3, 4, 5. I can have 3, 4, 5, 6. This going this way. 27, 28, 29. 30. And then I can't start with 28. It can't be, because then it will exceed 30, right? So then these are the number of subsets with 4 consecutive elements. How many ways I can select 4 consecutive elements? 27. Total numbers are 30C4. Out of these 30C4, there are 27 ways of selecting 4 consecutive elements. There are 27 ways of selecting 4 consecutive numbers. So subtract 27 from 30C4. You will get those number of ways in which no 4 are consecutive. From the total, subtract from the total 30C4, remove those in which 4 are consecutive. There are 27 ways of selecting 4 consecutive numbers. Remove those, you will get the number of ways of selection of 4 elements in which no 4 are consecutive. No 4 are consecutive. Right? Are you alright with this? NC4, NC5, NC6 are in AP. What's N supposed to be? Which means NC4 plus NC6 must be 2 times NC5, isn't it? Right? Which means NC4 by NC5 plus NC6 by NC5 must be 2. No? Dividing by NC5. Clear? You lost? No? So then, now look at this. NC4 by NC5. This is like n factorial by n minus 4 factorial by 4 factorial, n factorial, n minus 5 factorial by 5 factorial. Yes or no? N factorial would get cancelled. 5 factorial by 4 factorial will be 5, and then n minus 4 factorial is like n minus 4 into n minus 5 factorial. Yes or no? N minus 4 factorial is n minus 4 into n minus 5 factorial. So n minus 5 factorial will get cancelled. You will be left with n minus 4. Right? So NC4 by NC5 is 5 by n minus 4. Similarly, NC6 by NC5. NC6 by NC5 is n factorial by n minus 6 factorial by 6 factorial into n factorial by n minus 5 factorial by 5 factorial, right? Now this n factorial will get cancelled. 6 factorial is 6 into 5 factorial is 6 into 5 factorial. So 5 factorial will get cancelled. You will be simply left with 6. Yes or no? And n minus 5 factorial is n minus 5 into n minus 6 factorial, n minus 5 into n minus 6 factorial. So which is n minus 6 factorial will get cancelled. You will be left with n minus 5 in the numerator. So it becomes n minus 5 by 6. Yes or no? Clear? So plugging in the same, 5 by n minus 4 plus n minus 5 by 6 equal to 2. Multiply, solve for this quadratic in n and tell me what you get for n. 7 and 14. Alright, so n then, as she says, turns out to be 7 and 14. Two permissible values of n, 7 and 14. Right? Got me? In 6, alpha is like a MC2. We want to find the value of alpha C2. We want to find the value of alpha C2. Right? Alpha is MC2, which is like m factorial by m minus 2 factorial by 2 factorial, which is like m into m minus 1 into m minus 2 factorial. The m minus 2 factorial will get cancelled, divided by 2 factorial. So alpha is m into m minus 1 by 2 factorial, yes or no? No. Now alpha C2. Alpha C2 is m into m minus 1 by 2 factorial into C2. No? And what we just realized is NC2 will turn out to be n into n minus 1 by 2 factorial. Right? NC2 is n into n minus 1 by 2. Right? So this is also n, which is this, NC2, which would be n into n minus 1 divided by 2. This is NC2, which would be n into n minus 1 by 2. NC2 is n into n minus 1 by 2. So this is like NC2 n into n minus 1 by 2. No? Which is m into m minus 1 by 8, and this is like m squared minus m minus 2. Yes or no? Right? Which can be factored as m into m minus 1. This would be like m plus 1 into m minus 2 divided by 8. Right? Which is like m plus 1 into m minus 1 into m minus 2, and then multiply with a m minus 3 factorial so that the numerator can become m plus 1 factorial, so that the numerator could become m plus 1 factorial. Yes or no? Can I write this as 3 by 24? 24 is 4 factorial. 24 is 4 factorial. Yes or no? 24 is 4 factorial. So this is like 3 into m plus 1 by m minus 3 is actually m plus 1 minus 4 by 4 factorial. Yes or no? M minus 3 is M plus 1 minus 4. Hey, then what is it? N factorial by N minus R factorial by R factorial, right? Isn't it? This is N factorial by N minus 4 factorial into 4 factorial. So is it not M plus 1 C4? Is it not M plus 1 C4 by definition? Isn't it? So this is 3 times M plus 1 C4. Got me? बोलो कंफ्यूजन है थोड़ा ऑप्शन क्या है जो ये है वही है नन ऑफ दिस भी नहीं है क्या हाँ वो ऑप्शन है ना फिर नन ऑफ दिस भी तो हो सकता है ना नो वन टोल्ड हैज एनीवन एवर टोल्ड यू नन ऑफ दिस कांट बी एन ऑप्शन one of the mock tests last year, I do not know how it happened, but that was for class 12 last year. The batch that passed out in 2012. In one of their mock tests, I do not know what made me do that, but I might have been in a terribly bad mood that time. But the first 14 problems were all none of these. I mean, after the first 3, when they found the 4th also, none of these, they thought something must be wrong with them. They didn't realize that, well, something could be wrong with me at the time I gave them those options. So, but then, that's the test of mental strength. Confidence in yourself. If you're getting none of these, damn it, it is none of these, So, I still found one person, one guy from Frank Anthony, Manav Kedia, he was for sure a bumper guy. His final day didn't go that well, but he was awesome. I mean, he should have been in the top 50. But then I know out of these 14, he went all the way to 12, and then he got a little circumspect and little tentative, and he didn't mark. But then 12 were all none of these that he marked. That was very impressive for someone to actually, and he had a very high score in that test. But then all others stopped functioning after the 5th problem. They said, well, they can't, they were blanked out. This could happen, sometimes it could happen because the paper setter is crazy. This could, or he might have had a bad day at office. It could have happened. One of the things that I want to mention is, can I have your attention please? If for a certain problem, you fill out n spaces. The moment you start filling out spaces, it's a case of permutation. That means you are building order in the selection. So these are n spaces. You fill out space 1, you fill out space 2, you fill out space 3 for a certain situation, right? And you fill out space 1 and 2 and 3 and n, let's say in x ways. Now this x ways would bring order in the selection, because every time filling of spaces is done, you are building order, right? Then it becomes a case of permutation. The order in which these things appear here would get built into it. Now, after having filled out these spaces, you suddenly realize that the order was not important. After having filled out these spaces, you make a certain selection for space 1, you make a certain selection for space 2, you make a certain selection for space 3, and you make a certain selection for space n. And then you find out the total number of ways of filling out space 1 and 2 and 3 and n, and you find it to be x ways, right? And in this x ways, the order becomes almighty, right? Order in which things appear, selection for 1 and selection for 2. And then you suddenly realize that this was a case in which the order was not important. The order was not important, but we've already found x ways. And you have built order into it. Now, you want to suppress that order. You want to suppress that order. Who's whistling? Squeaky, crazy noise here and there. If you want to suppress the order, then you divide by n factorial and the order gets suppressed, This is what you do. If you found x ways of filling out these spaces, and after which you realize that the order was not in point of selection of 1 and selection of 2 and selection of all of these, you divide by n factorial, you would obliterate the order of appearance of these items. You divide by n factorial. Right? There are n white balls and n black balls, numbered 1, 2, 3, etc. n white balls and n black balls. If they are numbered differently, you can treat one black ball different from another black ball, one white ball to be different from another white ball, right? Because they are numbered now. Now we want to arrange these balls in a row so that neighboring balls are of different colors. Now, the arrangement could start with a white ball or it could start with a black ball. Suppose it starts with a white ball. Then it's going to be white, black, white, black, white, black, etc. White, black. This is how it could be, right? It starts with a white ball. So what we do is, if it starts with a white ball, first of all, the n white balls to be arranged in n spaces first. What I do is, I don't take cognizance of the black balls. These are the n white balls and I arrange them in n spaces. In how many ways would I do that? N factorial ways, right? So first of all, I just start with a white ball and I arrange them in n spaces, and that I could do in n factorial ways. That I could carry out in n factorial ways, right? Now, the n black balls would have to be arranged in these spaces. Now, between n white balls, how many spaces are there? There are n minus 1 spaces here plus 1 space at the end. So how many spaces available? N spaces in all. Yes or no? White, n white balls, and between them there are n minus 1 spaces and 1 space at the end. So there are n spaces in all, and in these n spaces the n black balls would have to be arranged. In how many ways can I arrange those? In n factorial ways, right? So first I arrange the white balls in n factorial ways, and then I arrange the black balls in n factorial ways in these spaces, so that no two white balls or no two black balls are consecutive, right? So n factorial ways, whole square ways, in which white comes first, Similarly, you could start with those cases in which black comes first. If black comes first, then black, white, then the same thing will hold good. So you would still have, if black comes first, you'll have n factorial whole square ways in which black comes first, n factorial whole square ways in which white comes first. So total number of ways is going to be n factorial whole square plus n factorial whole square, which would be 2 into n factorial whole square, 2 into n factorial whole square, in which certain cases would be there in which white comes first, certain cases in which black comes first, but there, in all cases, they alternate. No two consecutive white or consecutive blacks appear, right? Number of ways of dividing 2n people into n couples. 2n people that means number of ways of creating n couples out of 2n people. Number of ways of creating n couples out of 2n people. What I do is, let me create n slots. Let me create n slots. N slots, right? Now from 2n people, first I select 2 people, right? And place them here. In how many ways can I fill slot 1? 2nc. 2nc, 2 ways of filling this. 2 people selected as a couple and placed in slot 1, right? How many people remain? 2n minus 2. And then to select 2 more from them is 2n minus 2, C2 ways. So number of ways of filling out this spot is going to be 2n minus 2, C2, right? And then how many people remain after this selection? 2n minus 4 people remain. Number of ways of filling out this space is going to be 2n minus 4, C2. Yes or no? Similarly, next you will get as 2n minus 4, C2. Going this way, I'm sorry, 2n minus 6, C2. And eventually, for the last slot, there will be 2 people left, 2 C2 ways. Just prior to this, you will have 4 C2. So, a couple selected and placed in slot 1. Number of ways in which slot 1 could be filled is 2n C2 ways. Number of ways in which slot 2 could be filled is 2n minus 2 C2 ways. Number of ways in which slot 3 could be filled is 2n minus 4 C2 ways. I'm creating couples and I'm arranging them. I'm building order into the selection. I'm building order into the selection. Right? The first couple, the second couple, the third couple, the nth couple. Right? And I'm placing them in slots. Right? So first of all, number of ways in which I could select couples and arrange them in these n slots. Number of ways in which I could select couples and place them in these. This is selection and placing. Selection and placing in these slots. Selection and placing in these slots. Number of ways in which I could select n couples and position them in these slots is this into this, into this, into this. These are the number of ways in which the n couples could be selected and placed in these slots. That means could be ordered. The n couples are selected and then they are ordered in these slots. The moment you fill out these slots, you are building order. But then when you are selecting n couples, the order should not be important. Right? When you are selecting n couples, the order should not be important because they are not going to do march past, left, right, left, right. So then you want to, this is like you are creating a march past order. two couples, one couple, two people here, one couple in this position, another couple in this position, another couple in this position, selected and placed. So this into this into this into this is number of ways in which n couples be selected for a march past. These are number of ways in which n couples could be selected for a march past. 2 in row 1, 2 in row 2, 2 in row 3, 2 in row 4 and so on and so forth. Right? So a column is created of n rows. Fine. But that's not important. You're not selecting them for a march past, so you want to suppress the order of selection. How do you suppress the order of selection? Divide by n factorial. Divide by n factorial. That's how you suppress the order of selection. That's what I told you a little while ago. So divide this by n factorial. Divide this by n factorial. Got me? Huh? There are n slots, so it's like, no, you're confused? There are n slots, so no. So divide by n factorial, you get this. So you have like a 2n factorial by 2n minus 2 factorial here by 2 factorial. So this 2n minus 2 factorial will get cancelled with a 2n minus 2 factorial in the numerator of this. This will give me like a 2n minus 2 factorial by 2n minus 4 factorial by 2 factorial. The 2n minus 4 factorial here will get cancelled with a 2n minus 4 factorial there. And so on and so forth, right? So this numerator denominator cancellation would occur. And with each of these, there is a 2 into 2 into 2 into 2 into 2 n times. So 2 to the power n will appear anyways. So then what you have here is, this 2n factorial will not get cancelled, right? But the 2n minus 2 factorial here will get cancelled with the 2n minus 2 factorial there, and so on and so forth. Divided by 2 appearing in the denominator of each of these n times, so 2 to the power n. And then this is the divide and conquer. Right? N factorial. This is the number of ways in which n couples be selected out of 2n people. Which part? Everything. This you understood? You understood why I divided by n factorial? This is 2n factorial by 2n minus 2 factorial by 2. This is 2n minus 2 factorial by 2n minus 4 factorial by 2. So the 2n minus 2 factorial here and the 2n minus 2 factorial in the denominator of this will get cancelled. But the 2 here and the 2 in the denominator of this will stay. Similarly, the denominator of this is 2n minus 4 factorial. The numerator of this is 2n minus 4 factorial. So the denominator of this will get cancelled with the numerator of that? No. And that goes on. So all that which does not cancel is the 2n factorial here. Everything else will get cancelled. The 2n factorial and then the 2's here in the denominator will make it 2 to the power n. हर एक के साथ एक 2 है. So 2 into 2 into 2 in the denominator, 2 to the power n and the n factorial. What the fuck have you been up to? Get out! No, don't act innocent. I've asked you to not disturb my rhythm in the class by Have you all understood this? There's another way I could have looked at it, you know. Same thing. I'll be happy if you understood this, what I'm about to say. But even if you don't understand it right now, revisit this. I'm not going to, kind of force it down your throat at this point of time. Although it's not difficult, but I'm not sure if you've gathered enough maturity to understand. What I do is the following. There are 2n people, right? I just arrange them in 2n factorial ways in a line. That's what I do first. And then for each of these 2n factorial ways, I carve out these slots for couples. There are 2n factorial ways, way 1, way 2, way 2n factorial. There are 2n factorial ways, of which this is one, for example, right? In each of these 2n factorial ways, for example, let's say there is a pi pj appearing like this, and there is a pj pi that could also be appearing. But that should mean the same. That should mean the same. So for each of these, although in this 2n factorial, pi pj and pj pi are different, but they should be the same, right? That means if pi pj appears here, then this slot you should divide by 2 so that only one of them is counted, right? For this also you should divide by 2 so that only one of them is counted. This also you should divide by 2 so that a pi pj is the same as pj pi appearing here. No. So this also you should divide by 2. Each of these slots you divide by 2. That's one thing that you do. And then again there are n of these slots, and to suppress that count of arrangement you divide by n factorial. If you've not understood all of it, don't worry about it right now. Visit this in this perspective towards the end of combinatrix, right? Ideally I would have liked you to understand this, but even if you've not understood everything that I've said in this mode of counting, visit this in the later part of combinatrix, right? Keep this in mind and visit the situation in light of what I just explained. Clear? Number 9. There are 10 candidates A1, A2, A3, A10, and they have to be ranked. That means arranged. Ranked means they have to be arranged such that A1 is always above A2. Not right above A2, it could be just above A2 anywhere. For example, if A1 is here, A2 could have been here. So A1 is above A2 always, right? Not just one position ahead of A2, it could be one or more positions ahead of A2, right? You know what the situation warrants? I want to rank A1, A2, A3. That means arrange them, let's say, in n slots. Arrange them in n slots, 10 slots in this case. A1, A2, A3 to be arranged in 10 slots, 1, 2, 3, 10 slots, such that A1 is above A2, right? First of all, in an unrestricted manner, in how many ways can I arrange these 10 people in 10 slots? 10 factorial ways? Now, in half of these ways, A1 will be above A2, in the remaining half, A2 will be above A1. Yes or no? In half of these, A1 will be above A2, in the remaining half, A2 will be above A1. In half of 10 factorial, A1 will be above A2, in half of 10 factorial, A2 will be above A1. Very simple. So half into 10 factorial makes sense to you, right? Nahi samjha. Total 10 factorial ways. W1, W2, W2 up to W10 factorial, right? And exactly half of them A1 will be above A2. And the remaining half A2 will be above A1, isn't it? So half into 10 factorial. No? Are you confused? No? You were absent in the last class. Yes. Why? School exam. Did you write your name? Okay, half of 10 factorial then, right? Okay, answer this question. There are n points selected on a circle. N points selected on a circle, right? And any point is joined to any other point. All points are joined to all other points. All points are joined to all other points with all other points. P1 is joined to P2, P1 is joined to Pn, P1 is joined to P4 and so on and so forth, right? For example, P1 is joined to P3, P2 is joined to P5. There is one point of intersection. There is one point of intersection, right? Similarly, P3 is joined to Pn and Pn is joined to P4. So when 2 points is yet another point of intersection, right? Right? When points are joined to each other, all points are joined to all other points. There are various intersection points produced. There are various intersection points produced, isn't it? And it's given that no two intersection points coincide. It's given that no two intersection points coincide. All points are joined to all other points. All points are joined to all other points. Such that a large number of intersection points are created and no two intersection points are coincident. How many intersection points are created? How many intersection points are created in the process? How many intersection points are created? I hope you understand the problem. All points are joined to all other points, leading to a bunch of intersection points. How many intersection points in all? How many intersection points in all? Now, do you realize that every time you select a quadrilateral on the circle, that means you select 4 points on the circle, one intersection point is generated, isn't it? Every time you select 4 points, there is one intersection point created. There is one intersection point created. For every set of 4 points, one intersection point is created. How many set of 4 points exist? NC4. So these many intersection points. No? These many set of 4 points could be selected And for every set of 4 points, there is one intersection point. So these many intersection points, NC4, no? No? NC4, right? There are P positive signs and N negative signs where N is less than or equal to P plus 1. And we want to arrange these positive and negative signs in a row so that no two negative signs are together. So what we do is, let me first just arrange the positive signs. There are P positive signs, P positive signs. There is only one way in which I could arrange the P positive signs, right? Yes or no? There is only one way in which I could arrange the P positive sign. Now, the negative signs can appear only in these spaces, The negative signs can appear only in these spaces. Only in these spaces. Yes or no? Right? Now, across these P positive signs, how many of these arrows are there? P minus 1. And 1 at the end, P. And 1 here, that is P plus 1. There are P plus 1 eligible locations. For placing the negative signs. Right? The negative signs can be placed in these P plus 1 locations. Yes or no? So out of these P plus 1 locations, how many do you want to select for negative signs? N. In how many ways can you do that? P plus 1 C. So in these many ways, the signs could be arranged such that no two negative signs come consecutively. Yes or no? If they are arranged where these arrows are, the negative signs cannot be consecutive. Yes or no? They would always be separated by one or more plus. Clear? A, B, C, etc. are M plus 1 distinct primes. These are M plus 1 distinct primes. And we have a number which is A to power N, B, C, etc. And we want to be able to find out the number of factors. Of this number. Okay. So to create a factor of this number, I can select like a power 0, A power 1, A power 2, A power 3, A power 4, A power n. So then there are n plus 1 ways of dealing with this A. Either I can select a power 0 or a power 1 or a power 2 or a power n. So n plus 1 ways of dealing with this. And then there are two ways of dealing with B. Either select or not select. There are two ways of dealing with C. In a factor, either select that C or don't select that C. And how many, if there are m plus 1 in all, primes, then if this is n, then how many are remaining? M plus 1 minus 1, that is m remain, right? So then it's like 2 into 2 into 2 into 2 How many times? M times. Because M factors remain, 1 has been used up as various powers of A. I can either select A power 0, A power 1, A power 2. So n plus 1 ways of dealing with this, 2 ways of dealing with this, 2 ways of dealing with this, and there are M such factors. So that makes it 2 into 2 into 2 into 2, that makes it 2 to the power M. So n plus 1 into 2 to the power M factors in all. No? Is that okay? I can explain again if you're lost. Didn't understand? Okay, now to create a factor of this number n, capital N. First of all, you'll have to include various powers of A. You can select A power 0, A power 1, A power 2, A power 3, all the way to A power n. So how many ways of dealing with A? N plus 1 ways. And then how many remaining factors? M. Why? Because there are total M plus 1 distinct primes. One of the primes is A. So the remaining must be M more primes. So then in a factor, B can either be included or not included. So do 2 ways of dealing with B, 2 ways of dealing with C, 2 ways of dealing, bless you, and so on and so forth, M times. There are M factors, so 2 ways of dealing with 1, second, third, and the mth prime. So 2 into 2 into 2 into 2 into 2. So that makes it 2 to the power n. Number of ways in which you could deal with the primes is the number of factors that you could generate, right? So n plus 1 ways of dealing with this, 2 to the power m, that makes it n plus 1 into 2 to the power m. Are you okay with this now? Sure. Two white balls, we'll assume that these are different white balls, right? 2 white balls, 3 black balls, and 4 red balls in a box, right? The number of ways in which we can select 3 balls from the box, select 3 if at least 1 black ball is to be included in the selection. If at least 1 black ball has to be included in the selection. First of all, in how many ways can you select 3 balls without any condition? There are 9 balls in all. 3 balls can be selected in 93 ways. This is the total number of ways. In how many ways can you select 3 balls such that no black ball is included? No. In how many ways can you select 3 balls such that no black ball is included? 6C3 don't include, so you still have to select 3 from how many? 6. So 6C3 would give me the number of ways in which I could select 3 balls such that no black ball is included. So in these many, no black. These are the total number. From the total number I exclude those in which there are no black balls. Then I get those in which there is at least 1 black ball. So 9C3 minus 6C3 will give me those ways in which there is at least 1 black ball, right? These are three sides of a triangle and there are 3 points marked on AB, 4 points marked on BC and 5 points marked on AC. And we want to create triangles out of these interior points as vertices. With these as the vertices, I want to create triangles. How many triangles can we create in the process? How many triangles could we create in the process? Okay. What I could do is, one way to create a triangle is, I could select 2 points from here and the third from either here or, right, 2 points from here, third from here or 2 points from this and the third from this or, right, you know what I'm saying, or 1 point from here, 1 point from here and 1 point from there. Yes or no? Right. Now tell me, in how many ways? You want to just scribble for a while and check how many triangles could be created? Okay, stand by that. Alright, the result, so the previous problem 205, I can see quite a few of you have got it right, so very good. The result of 21 football matches and the possible results are win, lose or draw. There are 3 possibilities for each match, win, lose or draw. And the number of different forecasts that contain exactly 18 results, 18 correct results, okay. Which means out of these 21, you have to select 18 in which you've done a correct forecast. You've done a correct forecast. That means, first of all, 21C18 in which the forecast is correct. In which the forecast is correct, right? Now, there are 3 remaining football matches for which the forecast is wrong. So, first of all, select the 18 in which the forecast is correct. That you can do. For each of these, you can do it in one way. And for 21C18, these are the number of ways in which you could select the 18 matches in which the forecast is appropriate, right? Now, the remaining 3 matches, let me say F, F prime and F double prime. You made an inaccurate forecast, right? Inaccurate forecast means for any football match, these are the remaining 3 football matches, F, F prime and F double prime. Your forecast is incorrect. Incorrect means the correct forecast is only in one way, but the incorrect forecast can be in 2 ways, because there are 3 possibilities for a match, of which 1 is correct, 2 are incorrect, right? So the incorrect forecast for this match can take place in 2 ways. The incorrect forecast for this match can take place in 2 ways. The incorrect forecast for this match can take place in 2 ways. So 2Q ways in which the incorrect forecast could be carried out for the remaining 3 matches. So 21C18 into 2Q. That's the number of ways in which 18 correct forecasts could be made. The 18 matches in which the forecast is correct is like selecting 18 out of this 21C18, right? No? There are 3 remaining matches F, F prime, F double prime for which the forecast is incorrect. Incorrect means for each incorrect forecast there are 2 possibilities, because there are 3 options for a given match, of which 1 is correct and the other 2 are incorrect. So the incorrect forecast for F is in 2 ways, for F prime is in 2 ways, for F double prime is in 2 ways. So for the remaining 3 matches, the incorrect forecast can take place in 2Q ways, right? Now, my back is buckling today for some reason. For tomorrow, tomorrow is Mahalaya and it's a holiday for all of you. So, let's meet at 3 o'clock tomorrow. Or maybe 4 o'clock tomorrow. Let's meet at 4 o'clock tomorrow. Right? Let's meet at 4 tomorrow instead of 6. We'll continue with physics, work, power, energy from where